Hi class, hope you all are doing well, staying safe. Think I got my technical difficulties fixed here, so here's hoping it works. Got a kind of a weird setup going right now. You notice I got the PowerPoint here on the board. That's coming from my regular laptop. Using one of the school laptops to record, so maybe not quite as high quality. As far as the recording, hopefully everything is legible. I'm going to try to write big, all that good stuff. But what we're going to be covering today, guys, is optimization, some more of that. We looked at that a little bit before all of this started with the virus. We're going to look at it a little bit more now. Optimization, the idea of minimizing or maximizing some quantity. And so those are our objectives. We've got two of them. We want to be able to solve problems that involve both minimization and maximization. We want to be able to find the maximum value given a context. We want to be able to find a minimum value given a context. Those are our two goals for today. The difference is dealing with these objective functions. Now, an objective function, and I'll post the slides if this is too small. Those will be posted as well. I think you can hopefully read them, but an objective function is just a function, it comes from a context. So from a context, we write this function, and that function, then we will then use that to solve a problem. That is the idea of an objective function. In our case, our objective function will be a function that we're going to try to minimize or try to maximize, right? Those are our two goals here. So in section 4.4, before this all started, before we started working from home, we solved optimization problems where we were given an objective function. For example, the height of a rock is modeled by blah, blah, blah. We're going to use that equation to find the maximum height of the rock. Something like that. The difference between 4.4 and 4.5 is that now we've got to write our own objective functions, which can be a little bit tricky. It takes a little bit of practice. Your assignment's not going to be super long this week, probably 5 or 6 problems, I think, just because it is a little bit more time consuming. Thinking through the objective function can be a little bit challenging at first, but we're going to write those ourselves. Let's see, are you going to be able to read that? I don't know. I hope so. If not, again, it will be posted as well as it is in the textbook too. But your guidelines, the things that you want to do when we're writing an objective function, we're solving an optimization problem. All right, the first thing we do, we look at each variable. The equation is going to be talking about certain variables. So for example, we think about a rectangular box. It's not going to explicitly tell you the variables, but you have a length, a width, and a height there. So each variable that mentions in the problem, you're going to give it a variable. So for length, width, and height, maybe I use L, W, and H, perhaps. If it's appropriate, which it almost always will be appropriate, by the way, you're going to draw and label some kind of figure. Drawing a picture is going to be extremely important when we solve these problems. Number 2, the second thing, once we've drawn our picture, once we've made our variables, we want to try to find an expression for the quantity we want to optimize. So maybe we're trying to optimize a surface area. Maybe we're trying to optimize a volume. We could be optimizing any number of things. We're going to try to find an expression for that quantity. Now, step 3. We're going to have conditions that are given in the problem. We're going to use those to write the quantity as a function that only has one variable. Okay, so we're going to write functions with only one variable. We're not going to worry about implicit differentiation here, anything like that. We're going to try to write one function with one variable is our goal. And then we also need to make sure that we're aware of any restrictions that we've got to place on the domain. So for example, with a box that we've been talking about, the length, the width, the height all need to be at least 0. You can't have negatives, lengths, widths, or heights. That'd be an example of a restriction on the domain due to physical considerations. That's the most common restriction that we're going to deal with. And then number 4, we're going to optimize using the strategies we looked at back in section 4.4. So first derivative test to find critical values. Second derivative test to tell whether they're mins or maxes, and or looking at the graph of the function. So those are the two things that we're going to be doing there in terms of optimizing. Moving forward then, let's take a look at a maximization problem. This type of problem should feel familiar to you thinking back to pre-calculus. This is applied example 1 out of the textbook. You're probably, I'm guessing, following along maybe on your phone with the slides, something like that. We got a man, he wishes to have a rectangular shaped garden. Let me move this in a little bit because that does look a little bit small to me. See if that helps. A little better, okay. Hopefully we can read that. But a man wants to have a rectangular shaped garden in his backyard. He's got 50 feet to work with to enclose that garden. We want to find the dimensions of the largest garden that he could possibly make. And again, this should feel familiar, thinking from pre-calculus last year. Or in college algebra, I think we saw it too. We looked at this in terms of, obviously not using calculus. There, we're going to look at it with calculus here. So we've got this drawing, which I believe I've got on there. I do. We've got a rectangle. Here's his field. I'm going to draw these x's and y's a little bit bigger. We'll say here's x, and here's y. Is that big enough? Looks big enough, yeah. All right, so the restrictions that we have. Well, first off, he's got 50 feet of fencing to work with. Let's deal with that part first. The drawing actually, it created the variables for us. The variables are x and y here for the height and the width, if you will, or length and width. We know that this 50 feet of fencing, that deals with around the outside of the garden. That's a perimeter. And so we know that 2x plus 2y needs to equal 50 feet. All right, so you take 2x, you got the x here and the x here. You've got 2y, a y down here and a y up here. We add those together, they've got to be 50. Now, what I'm going to do is I'm going to solve this equation for one of these two variables. So subtracting 2y from both sides, and then dividing by 2, we can see with a couple steps of algebra that x equals 25 minus y. Okay, so we solved this equation for x. We have x equals 25 minus y. Now, the next function. The next function, we want to maximize. This is my objective function. We want to maximize the area, which is equal to x times y. Okay, to find the area of a rectangle, we multiply length by width. We know that. And so to maximize it, that is going to be our goal. We're going to want to find dimensions for the largest garden. That's our keyword, the largest garden. We're maximizing this area. But this has two variables. Remember, step 3 said to write it as an equation with one variable. Well, the way we do that, that's where solving this equation for x comes in. Now that I've got x by itself, I can use substitution into this equation using the physical constraints that I had from the 50 feet of fencing. So area will equal x times, no, y times 25 minus y. That's substitution there, which is equal to 25y minus y squared. So we want to maximize that function. We're going to maximize that function right there. And so remember, the way we do that, we use the first derivative test to find any critical values. Okay, so we're using the first derivative test, so I got plenty of room off to the side, I'll do that. So first derivative test, so a prime is going to equal, well, the derivative of 25y minus y squared, that's going to be 25 minus 2y. The derivative there is 25 minus 2y. I want to set that equal to 0, right? Remember, the first derivative test says to set the first derivative equal to 0. Those are your critical values. So let's see here, 25 minus 2y equals 0. We can get pretty quickly there that y equals 12.5 feet. And then we use my value of x here. X is equal to 25 minus y. So x equals 25 minus 12.5, which is also equal to 12.5 feet. And thinking back to pre-calculus, that was that shouldn't surprise us. We found that the optimization for a rectangle was usually to make that rectangle a square in a circumstance like this. And so it does make sense in this case that the x and y are going to be the same. Those are the dimensions that will maximize the area. All right, let's go ahead and take a look at another one. Let me first clear off the board here. And then we'll look at a second optimization problem. All right, where's my remote at? Let's do it that way. So there it is. Okay. So now, we've got a packaging problem, which I believe this is also familiar from either college algebra or pre-calculus. I think we looked at something similar to this one too. So basically we've got a company that are cutting away identical squares from each corner of a rectangular piece of cardboard. So we got this piece of cardboard, we're cutting out corners here that are all the same size. We're going to fold them up, we're going to make a box. All right, an open box, which means there is no top of the box. So we're going to, let's see, where was it? Oh, we're folding up the resulting flaps. We're going to make it into an open box. The cardboard is 16 inches long and 10 inches wide. We're going to find the dimensions of the box that will yield the maximum volume. So we're maximizing volume. So let's see here. Let's start with variables. Let's see here. Well, for a volume of a box, there are three variables that are important to us. So let, this time the drawing's not going to be given to us. Let L equal the length. Actually, scratch that. I think I have drawings in here. Take a look here. Yeah, I got a drawing here. Okay, so this drawing does most of the legwork for us mathematically. I do want to explain where it's getting these values. So it may look kind of like a jumbled mess on this particular slide there. It's a little bit small. Take a look at it in your book or on the slides there. It's a little bit bigger. But the entire cardboard is 16 feet wide, 10 feet tall. But we cut out x by x squares in each corner. That's the idea, that we're cutting away identical squares from each corner. So each of them is x by x. Now, I don't know what x is, but I do know that I'm cutting it off of each corner. And so I've got 16 all the way across, but I cut off x here, I cut off x here. The result is that my new width is 16 minus 2x. Okay, I had 16, I cut off 2x. Likewise, I've got 10 minus 2x. Now, I can fold this box up. When I do that, it looks like this. Yeah, there we go. So I can see that the length is 16 minus 2x. The width is 10 minus 2x. And the height is just x. Okay, so I've got my three dimensions there. So this is the drawing, the picture, the creating of the variables. Now, my objective here is to maximize volume, which is equal to length times width times height. Okay, that is my goal. I want to maximize the length, the width, and the height. So, look at this. That's going to be equal to x times 16 minus 2x times 10 minus 2x. Which, multiplying that out, let me just get on Wolfram Alpha and check that out. So, I don't feel like doing that math right now. X so 4x cubed minus 52x squared plus 160x. All right, back into the PowerPoint. There we go. Oops, and let me just get those drawings back on the board there. There we go. So we want to maximize the equation, the function, 4x cubed minus 52x squared plus 160x. So to do that, we'll use the first derivative test again. So the first derivative test here, and we'll say v equals, so v prime, do I have room over here? Yes, I do, just a little bit. So v prime, is that going to fit? Yeah, just barely. Okay, so v prime is equal to, let's see, the derivative of that function over there is 4 times 3 is 12. X squared minus 104x plus 160. Again, I don't really feel like taking time to try to factor that or quadratic it. Let's just use Wolfram Alpha real quick. So let me just do that. We're going to set that equal to 0 and solve it. So solve 12x squared minus 104x plus 160 equals 0. Let that take care of it. X equals 2 and x equals 20 over 3. So there are 2 possible answers. So either x equals 2 or x equals 20 over 3. Now, there aren't actually 2 values that are going to maximize this function. Only one of these will be a maximum, right? There aren't going to be 2 maximum values. There's only one. So it's either going to be 2 or it's going to be 20 over 3. We've got to figure out which. Cue the second derivative test. All right, we're going to use second derivative test. We're going to take the second derivative. So v double prime is equal to 24x minus 104. So plugging in each of these, v double prime of 2 is equal to 48 minus 104. Let's try that. 48 minus 104. Negative 56. That is a maximum. Remember, when the second derivative is negative, you have a relative maximum. When you have a second derivative that is positive, like I believe we'll have with 20 over 3, you'll have a minimum. Let me just check that real quick just to confirm. So v double prime of 20 over 3, 24 by 20 over 3 minus 104 is positive 56. So that is a min. So we can see here that there is a maximum when x equals 2. So now we got to find the dimensions of the box. So x equals 2. So let's find those dimensions. And put the pictures back up. Where did I put that? Right, there it is. Here are the pictures. So we can see that one of the dimensions is just x. So it is the dimensions are 2 inches by, let's see here, 10 minus 2 times 2. So 10 minus 4 is 6 inches by 16 minus 2 times 2 is 12 inches. So the maximum volume that you can get out of this is 144 cubic inches. It doesn't ask for that, but we found the dimensions there. All right, that's maximization. I do intend to put up a couple more examples on Overleaf. I just need to get around to typing those up. Look for that to happen here in the near future. Just got to find time to get that done, probably after lunch here. Let's move into minimization, which is the same concepts, except for now we're trying to minimize instead of maximize. We're going to do the same thing. So let me just do a little clearing. All right. So we've got a packaging problem. Lots of times companies want to be able to contain a certain amount of product using the least material. Why do they want least material? Least cost. They're trying to minimize the cost of producing an item. So here's an application of that. So Betty Moore Company requires that its corned beef hash containers have a capacity of 54 cubic inches. All right, so that is a requirement. Okay, so you got a capacity is a volume. Have a shape of a right circular cylinder, and they must be made of aluminum. We want to determine the radius and height of the container that requires the least amount of metal. That least amount of metal, that is a surface area. That's covering the outside of the can. So we've got a restriction on the volume. We want to minimize the surface area. That is our goal here. So we want to minimize, let's see right where my cylinder is. Let me put my cylinder up first. There we go. So I want to minimize the surface area here. The smaller the surface area, the smaller the cost. Now, I'm given a restriction on the volume. Let me give you a couple of useful formulas here with cylinders. The volume of a cylinder is the area of the base, pi r squared, times the height. And the surface area, the total surface area is 2 pi r squared. Okay, so that accounts for the top and the bottom, plus 2 pi rh. This middle area, that is a rectangle with a width of 2 pi r and a height of h. So, with these formulas, I can now try to create a function in one variable. I've got my variables are r for the radius here, by the way, and h for height. The problem creates those for me. So let's see here. So my restriction is the volume is equal to pi r squared h, which is equal to 54. Now, like in the previous problems, I'm going to solve this equation for one of my variables. And I can do that. Let's see here. So we'll solve that for h. H will equal 54 over pi r squared. Okay, so that is solving this equation for h. we divided both sides by pi r squared. H is equal to 54 over pi r squared. Now, we want to minimize the total surface area. So we want to minimize the objective here is to minimize surface area, which is equal to pi r squared plus 2 pi r, and we'll replace the h here with the 54 over pi r squared. So over 54 okay, so our objective here is to minimize this function, and let's simplify this a little bit. Okay, let's simplify this function out just a little bit. Let's see here, pi's are going to cancel. R's will cancel a little bit. So that's going to equal pi r squared plus 108 over r. Well, let's just go ahead and graph that one. We could do the first derivative test here to find the minimum value. Actually, let's go ahead and do that. Let's just do the first derivative test. So, surface area, its derivative. Let's see, am I still in bounds here? Yes, I am. So let's see, the derivative of this. The derivative here with respect to r is going to be 2 pi r. Thinking of this as an r to the negative first power, the derivative of that would be negative 108 r to the negative second power, using the power rule here. So this will become minus 108 over r squared. Now, what we want to do, we want to set this equal to 0. So set this equal to 0. So 2 pi r, let's see here. So 2 pi r minus 108 over r squared needs to equal 0. We're going to multiply both sides by r squared to get this r squared off the bottom. So we get, looks like 2 pi r cubed minus 108 is equal to 0. Let's see here. Feels like so. No, it's good. We're good. Let's see here. So 2 pi. So r cubed is equal to 108 over 2 pi. And so r is going to be about what? We'll have to take the cube root here of each side. Let me get a calculator to do that with. 108 divided by 2 pi. Take the cube root of that. 2.58 inches, and the height I can then plug in to here. So 54 over pi times r squared. I'll just use the A and S key on my calculator real quick. So it's going to be 54 over pi also 2.58. Something seems wrong with that. Let's see here. I did not think that was the answer. See if I'm missing something here real quick. So 2 pi r plus 2 pi RH, 4 pi r squared. Let's see here, that's all makes sense. That all makes sense. Let's see here, let's check it. Grab my book and just check that real quick. Something seems amiss there. That's not the answer I was expecting. So, actually, maybe it did. Let me take a look. So applied example 4 and 4.5. Oh, shoot. Let's see. There we go. Okay. All right, got some fixes to make. Reckless me here. Let's see. Had to change these 2's to 4's. I didn't write down the equation correctly. 2 pi r squared plus 2 pi rh. I didn't do that properly. So a 4 r cubed now is equal to, now where's it getting a pi from? That's my question. R cubed is 27. And so come back to this. So I've got a little error here. I got to find this. I will fix that. I'll put that as an extra one in my, I was 27 over pi. And so R is about 2 right there is the correct answer, and the height then is going to be 4. More or less. I will write this out thoroughly on Overleaf. Don't worry about fixing that right now, I wouldn't say. Sorry about that, something weird went wrong there in my mind. I will fix that like I said. So let me just clear the board here, and let's do one more. Clear this. Okay, what do we got next? So a pencil cup with a capacity of 36 cubic inches. Another restriction on volume there is to be constructed in the shape of a rectangular box, so a little bit easier maybe than a cylinder here, no pi involved, with a square base, so that's important, a square base, and an open top. That's also important, an open top. Can't have a pencil case with a closed top, so we're going to be missing a top. If the material for the sides costs 15 cents per square inch, and the material for the base costs 40 cents per square inch, what should the dimensions of the cup be to minimize construction cost? When I was first working this problem, I ran into some issues. I didn't realize that it had to be a square base. This square base piece is really important. Normally with a box, there are 3 dimensions, right? There's a length, a width, and a height. Well, the fact that this is a square base tells me there's only 2 dimensions because the length and the width are the same. The length and the width, maybe I'm going to say S, so the length which is equal to S. Okay, just for a side length there. So we've got one variable, which is S, which represents both the length and the width. And we'll say that the height is H. Now, a couple needful formulas for a box here. The volume of a box is equal to length times width times height. The surface area in this case, this is open, Well, there's only going to be one length times width. That is the bottom. Normally, for surface area, there would be a 2 in front of it, so there'd be a bottom and a top. But it's just going to be one length times width plus 2 length times height. That's, you know, the dimensions of one of the sides. And then plus 2WH. That's another one of the sides. I can't draw this rectangle, unfortunately. I'll try to do it in GeoGebra. Maybe do this in Overleaf as well, but can't draw that box right. But this is the equation. So we've got the following information. The volume, length times width times height. So volume is equal to length times width times height. Well, length times width is S times S, or S squared, is 36. So solving for H here, I can see that H is equal to 36 over S squared. Now, my objective in this function, or in this situation, is to minimize surface area, but I've also got to take into account these costs. So let's start with the base, the bottom. The base costs me 40 cents per square inch. So I'm going to say that's going to be 40 times the length times the width. The length times the width. So times S squared plus 15 times 2SH plus 15 times another 2SH. Okay, so I've got the cost times 2LH plus cost times 2WH. So that's going to equal 40S squared plus 60SH. But I can do substitution. I know that H is equal to 36 over S squared. So I've got equals times and I simplify that the rest of the way down. I'm trying to minimize the function 40S squared plus 2160 over S. So to do that, I'm going to take the first derivative test. So 40S squared, so let's see here, so SA prime is equal to 80S minus 2160 over S squared. And so now I do the same math I was doing before, except I don't screw up like I did last time. So let's see here. So 80S minus 2160 over S squared equals 0. Take both sides by S squared, so 80S cubed minus 2160 equals 0. 80s cubed equals 2160. S cubed is 27, and S is equal to 3. And I know that one's right. That is the correct answer for S, so I feel good there. Solving for S. Now, last step, find H. H is 36 over S squared, so 3 inches. The height is equal to 36 over 3 squared, which is equal to 4 inches. So the ideal dimensions are the length and the width must be 3 inches, the height must be 4 inches. So like I said, we do get a little bit into the weeds here. Sorry about that. There is a lot to this. I will probably go ahead and type these out as well, just because the handwriting's not as neat, maybe a little bit small in places, and it won't take me long to type it out. So I'll tack these into what I plan to do. You may not even need to watch this video, I guess, in that sense, but that's all right. Anyway, thank you for watching. I believe that does conclude the video. Make sure that is the end here. It is, so I'll go back. Thanks again. I'm going to go ahead and stop right there.